Okay, so we will have Olga Papadoulaki, who will tell us about an inflationary cosmology from anti-de Sitter wormholes. Please, the stage is yours.
Thank you. I would like to thank the organizers for organizing this very interesting workshop and for inviting me here and giving me the opportunity to present our work. So I will talk about an inflationary cosmology from anti-de Sitter wormholes, and this talk is based on this paper that we have in collaboration with Panos Begios, who is a postdoc at the University of British Columbia, and from this fall he will move to Ghent. As well as I will flash at the end a slide, if time permits, that is work in progress that we also have with Ioannis Yalamas, who is a postdoc based at Tallinn. So probably have to do it here. So let me give you some motivation why we are interested to find the wave function. So this is the history of our universe as we know it currently from observational data. So it started with a Big Bang. The time grows towards here. And we will be interested in the early cosmology up to inflation. So currently our universe is expanding. It's hot. It has a temperature around 2.73 Kelvin, so not Greek hot. And we have seen that it's extremely uniform on large scale. For example, the variation of the temperature over temperature is 10 to the minus 5. But what gave rise to such evolution and the form that our universe has currently? So there are many features of the early cosmic evolution that they were very puzzling. For example, the flatness problem, where we see that our universe is nearly flat and homogeneous and isotropic. The horizon problem, where we have noticed that causally disconnected regions of space-time are very similar. So since they are causally disconnected, we would have expected that they are very different from each other. So why there is this uniformity? We haven't observed any exotic particles such as monopoles, so they should be extremely diluted, as well as the primordial perturbations are nearly scale invariant. And inflation is a theory that explains these features and incorporate them very nicely, and as well as it resolves even more puzzles. But there are many questions, especially related to pre-inflationary issues. For example, what gave rise to such initial conditions that can lead to inflation? If we have a Big Bang and we have an initial singularity, we would expect that our physical laws, they don't work there. And if we want to understand the universe close to the singularity, probably we'll need a full quantum theory of gravity. But are there any ways that we could compute some features of the early universe without going to the full UV theory? So for example, is there any approximate way to compute or estimate probabilities and features of the early universe cosmology? So Hartle-Hawking gave one such appealing proposal for computing the wave function of the universe. Their work is based on the so-called Wheeler-DeWitt equation. And essentially what they do is that they use the canonical or Hamiltonian formalism of general relativity and promote the constraints that express the diffeomorphism invariance of gravity to quantum operators that annihilate the wave function. So let me give you some brief overview of the canonical formalism. So essentially, we are using the ADM decomposition by Arnovit, Deser, and Meissner to write our metric in this form, where n is the so-called lapse function, and then I is the shift vector, and Gij with small Latin indices is the metric that describes the spatial slice sigma. We start from the Einstein-Hilbert axiom, and we can also add a matter term. and the canonical Hamiltonian can be written in this form, where H and HI are the Hamiltonian and the momentum density respectively. This pi ij are the conjugate momenta to the spatial slice metric. And we also have the matter parts, and the covariant derivative is with respect to the metric on the spatial slice. Diffeomorphism invariance of the theory, it corresponds to the fact that the physical state should be independent of the Lambda shift function vector. And this leads to primary and secondary constraints. And the secondary constraints is that we should impose that the Hamiltonian momentum density should be 0. Since we're interested in inflationary models, the matter content of our theory will be a scalar field that will play the role of the inflaton. And now we want to go to the quantum level. So as we stressed a bit briefly a bit earlier, in the quantum level, we have to impose these constraints as operators that act on the wave function. So the Hamiltonian constraint takes this form, and the momentum constraint this. And this is essentially leads to the Wheeler-DeWitt equation. These equations are not really well defined, but there is a truncation, the so-called mini-superspace truncation, that essentially what we do is that the functions of the metric, they don't depend on all the coordinates, but only in the radial or time direction. And if we constrain to this mini superspace, these operators are better defined and they are self-adjoint, so we have a well-defined inner product. Fortunately, the fact that our universe is isotropic and homogeneous, it's good because these ansatz, these mini superspace ansatz make sense and could be physically relevant. So essentially, if we use this mini superspace ansatz, the Wheeler-DeWitt equation makes sense. So in this ansatz, the metric can be written in this form, where this is the Laps function, and this is the alpha t is the scale factor, and this is our scalar field. And in this case, the momentum constraint is automatically satisfied. So all that we have to do is to solve the Hamiltonian constraint, which is essentially a solution to the Wheeler-DeWitt equation. And one should provide appropriate boundary conditions to do so. So Hartle-Hawking proposed the no-boundary proposal that essentially tell us that we have to go to a Euclidean signature and consider all possible compact metrics with no boundary at early times. So we define our path integral over this type of metrics. And the state or wave function that one obtains in this way is the so-called Bunch-Davis vacuum, which we can think about it as the analog of the Minkowski vacuum, when we are in a cosmological setting, when lambda is positive. There is also an alternative proposal by Linde and Vilenkin, the so-called tunneling proposal, which essentially we tunnel to our current form of the universe from nothing. And this can be seen if we are in the superspace of all metrics, and we have some probability influx on the boundary of the superspace that drives this tunneling. So the simplest example is to not add matter and just consider the Einstein-Hilbert action with positive cosmological constant. And this case admits an empty de Sitter solution. So the Hartle-Hawking proposal classically describes a complex metric where from times up to pi half is Euclidean and is a sphere. So we have the half sphere. And after pi half, we analytically continue to imaginary time, and we end up to Lorentzian de Sitter that we glue here to the Lorentzian part, to the Euclidean part. So in the mini superspace, the Wheeler-DeWitt equation with positive cosmological constant and no matter takes this form, where pi alpha is the conjugate momentum to the scale factor. So we need to solve this equation. So to understand this, to understand its semiclassical properties, it's convenient to employ the WKB ansatz. And we have two possible solutions. One is Lorentzian and is oscillatory. And these SL are the on-selection in Lorentzian signature. And there is a Euclidean part that is exponentially decreasing and increasing depending on the branch. And SE is the Euclidean on-selection. So for large values of the scale factor, the wave function is oscillatory. And for small scale factor, it has an exponential decreasing and exponential increasing behavior. This black line here is the potential. So the potential is unbounded from below. That's why for large alpha, we have the oscillatory branch. And for small alpha, the no boundary proposal selects the increasing branch, and the wave function vanishes at zero scale, whereas the tunneling proposal would select the decreasing branch. So now one can include also scalar fields if we're interested in inflation, and moreover we assume a slow roll approximation for the potential in the inflationary region. So essentially it has to have a very small slope and curvature. And now the Wheeler-DeWitt wave function will depend, apart from the scale factor, also to the scalar field. So under the zero roll approximation for the potential, one finds the semiclassical no boundary solution here, where this P no boundary is given by the Euclidean part of the action, as well as the tunneling proposal that essentially selects the opposite branch, as we mentioned 2 slides ago. And these are the expressions for S Euclidean and S Lorentzian, which is the on-selection, the Euclidean on-selection for the sitter and the Lorentzian on-selection, so the oscillatory part. So apart from computing the wave function, one also can compute the inhomogeneous fluctuations of all the fields, so the scalar and the metric. And the no-boundary proposal predicts the correct spectrum of primordial perturbations with a Gaussian suppression. So this gives more credit to the idea that the no-boundary wave function is the analog of cosmological vacuum. Whereas, unfortunately, the tunneling proposal, for the tunneling proposal, the fluctuations are unsuppressed. Moreover, given the wave function, one can compute the probability for a specific history or realization of the universe by computing the norm of the wave function. And for the no-boundary proposal, the leading answer is this. And this, as we will see, leads in a very important problem in the context of population. And there are reviews on this subject by Lechners and Maldacena. So essentially, what this is, if we take the current value for the potential, is that this ratio is 10 to 120, which is the cosmological constant problem. But here is exponentially worse because we have it in the exponent. So essentially, the no-boundary proposal gives us an overwhelming probability for an empty cold universe with the smallest allowed number for the cosmological constant. And in the inflationary context, it predicts the least number of fifolds. So this issue stems from the fact that the on-selection for Euclidean de Sitter is negative. So minus and minus, we have plus here. So this is an important problem, and it should be so. Yes. Yes. So this is an important problem, and we need to find a way to resolve it. So one idea is to not use a no-boundary proposal. We use the tunneling proposal, which, since it takes the other branch of the Euclidean part, it has plus sign here, and as Euclidean is negative, so it gives a reasonable probability. But the problem is that it doesn't give the correct fluctuations beyond mini-superspace. Another idea is to evoke an anthropic reasoning and just use some selection rule that selects the value that we need for the current cosmological constant. Or we could say that whatever we describe here, it doesn't make much sense anyway, because the gravitational theory, the quantum gravitational theory, is non-normalizable, and in the Euclidean signature we have the conformal mode problem, so the action is unbounded from below. So one should do properly the path integral computation by going to complex space and using the Picard-Lefzer theory to define the appropriate contour to perform the path integral. And this is an active area of research that people are studying at the moment. Here, we will propose a different resolution, which is to change entirely the assumptions and setup that give rise to our cosmology. And I will argue now why. So let me do a brief detour in negative cosmological constant, when gravity is better defined and everything works nicely. So we know that if we have a negative cosmological constant, we have the holographic principle or asymptotic correspondence that tell us that the partition function of a quantum field theory or a CFT that lives at the boundary of, let's say, an asymptotically ADS space-time is equal to the path integral for the gravitational theory, in one extra dimension. So, for example, the analogous case of a non-boundary proposal is to have a global Euclidean ADS, which is a ball, so it has a regular interior. And then if we go and compute the partition function for the CFT at the boundary, so the boundary is an S3, and the partition function and the path integral for the global Euclidean ADS4, the answers do match. And if we also have supersymmetry, for example, if you have the ABJM theory, via localization, we can also compute the finite end result or Newton corrections, and these results still match. And the crucial difference is because we are on ADS space, after we perform holographic normalization, our own selection is positive. So we don't have this issue as in cosmological setups. But the bad thing is that this picture has nothing to do with cosmology. But there is a way to use the nice features of ADCFT and somehow connect them with cosmology. And this is via going through the description of Euclidean wormholes in holography. So let me give you just 3 slides that I give you some basic facts about wormholes in holography. I will start with Lorentzian wormholes. This is not what we will study in the following, but this is the better understood example. And the most well-known Lorentzian wormhole is the Einstein-Rosen bridge that connects the two sides or the two exteriors of the eternal black hole. This bridge also exists in the Kruskal case, so when we are asymptotically flat, but here we want to have holography and we want to have a quantum field theory that lives on the boundary of space-time, so we will focus on the ADS case. And in this case, the wormhole essentially is the equivalent of the Einstein-Podolsky-Rosen pair of two black holes in a particular entangled states between the two non-interacting quantum field theories that live on the two boundaries. And essentially, the energy levels of the two theories on the left and right should be entangled and be at the same energy level, and we sum over all this energy level. And essentially, from the QFT point of view, this tells us that a large amount of entanglement can give rise to a geometric connection. So to recap, wormhole solutions have two asymptotic regions. In the case of a spacetime with boundary, they have two asymptotic boundaries. And via holography, we interpret such a geometry as describing a pair of entangled but decoupled quantum field theories. We cannot pass a message through this wormhole because the boundaries are always separated by a horizon if we impose the null energy condition. And another way to see this is if we go to Euclidean signature, the space will smoothly cap off and we will have two disconnected cigar geometries. So essentially, in the Euclidean picture, entanglement cannot give rise to such geometric connection. We need something stronger, and also entanglement is not very well defined since there is no time direction if you are Euclidean. We can also construct traversable wormholes via violating the non-energy condition, so then we can send signals through the wormhole. And holographically, it was shown by Gauja, Ferris, and Wall that this can happen if we couple our two boundary quantum field theories via local interaction of this form, where OL and O right are operators on the left and the right quantum field theory. But as I said, we are interested in Euclidean wormholes. I will explain later why. So in the Euclidean case, there is no time direction. We only have Euclidean space, and we can picture the wormhole like this. We have two asymptotic regions, and since we are interested to have holography, these are asymptotically DS, so they have two boundaries, and there is a throat that connects these regions. And to create this throat in Euclidean signature, it's much, much easier than in the Lorentzian because to support it, we just need to have locally negative Euclidean energy. And this can easily be done by providing appropriate matter, for example, if we have axionic fields or magnetic fluxes. There are several solutions of this type in different dimensions and setups, and some of those can be embedded in the standard model plus gravity. And it is also shown that a subset of such solutions is perturbatively stable. In the following, we will restrict our study to axionic wormholes since we are interested in inflation and cosmological content, but the same analysis could follow for other matter content. Mm-hmm. You analytically continue. No, it's just that you need to have something that is negative. For example, another way to do it is you could slice your ADS with hyperbolic planes, and this can also give you something negative to support the throat. Mm-hmm. Yeah, I just mean that if you are in the Euclidean, like the term that will be giving you the energy, let's say if you have an electromagnetic field is E squared minus B squared, now this sign changes, right? And you need this term to be negative. Yes, exactly, yes. So, okay, I made a big detour. I went to negative cosmological constant. I told you about Lorentzian wormholes, Euclidean wormholes, how it is even connected with what I was saying before. So there is a way in holography to have examples of FRW cosmologies, and this is via two boundary Euclidean ADS wormholes. So imagine we have a wormhole with this metric. This tau is the Euclidean time, and zero. At tau minus n plus infinity, we have the two asymptotic ADS region, and zero is the middle of the wormhole. And at the throat, at the middle of the throat, we want the second derivative of the scale factor to be positive and the first derivative to be zero. So we have a local minimum there. And if we go now and perform analytic continuation on these Euclidean wormholes, there are two options. Either you can analytically continue one of the transverse directions, and then you get a traversable wormhole. But then you need to be careful because then you violate the null energy condition, and this could show pathologies in the matter content of your theory. For example, if you have gauge fields, you might get imaginary components that you cannot gauge away. Or you can go and analytically continue the Euclidean time or radial direction to Lorentzian time. And then you end up with a Bank-Ranch universe. This universe will crunch and you will not have enough time to see inflation. So, but maybe there is a way to combine features of the no-boundary proposal and Euclidean wormholes to get an inflationary universe, and this is what we will propose here. So this is the no-boundary proposal. We have the half sphere, and here we analytically continue to Lorentzian de Sitter. This is the picture I showed you before here. So you start by the Euclidean ADS wormhole, and in the middle of the throat, you analytically continue, but you can't. Or we can have this picture where we have the Euclidean ADS wormhole. The throat of the wormhole becomes minimal here, but we can impose such boundary conditions on the scale factor that it opens up again and resembles Euclidean de Sitter. And after a point, we analytically continue to Lorentzian de Sitter. So essentially, we glue the Lorentzian part of the universe here. And I will argue now that this picture can give us good conditions for inflation. So we'll call this half wormholes wine glass wormholes because of the shape they have. And their defining properties are the following. They should asymptote to Euclidean de Sitter at minus n plus infinity. And in addition, the scale factor in the middle, the second derivative of the scale factor in the middle should be negative, and the first derivative should be zero, so that we have a local maximum there, and the first derivative of the scalar field is zero there. And these could be good initial conditions for the subsequent inflationary evolution, since this essentially, when we go to Lorentzian, will change sign and become positive. So an example of a scalar potential that can support all these features is the following. So we start with Euclidean ADS, and then by relevant deformation, we can acquire a positive potential. And here we are in the point that we can analytically continue and have a period of inflation. And then we might also have a period of reheating, etc. But here we will discuss essentially this part, how we can arrive to good inflationary conditions via this picture. So you have anti-de Sitter up to here. Here you have Euclidean de Sitter, and from here on you have Lorentzian de Sitter. So essentially, you could have a total Euclidean thing. So this part is symmetric, so you can have another part here, but you cut it and you glue the sitter, as is in the no-boundary proposal, that you cut the sphere in the middle and you glue the sitter part in the classical picture. So what model can give rise to such wine glass wormholes? So a simple model is to consider an Einstein scalar action system. This is the three form that is dual to the action field. And this is the coupling of the action. We use a spherically symmetric and homogeneous ansatz. So the metric has this form. And the three form can be written like this, where Q is the charge of the action. And the two independent equations of motion are the following, and this is the equation of motion for the scalar field. Thus, as can be seen, it describes a particle that moves to a potential minus v of phi, and there is also a friction and anti-friction term depending on the sign of alpha prime here. So we consider a potential with a local maximum at phi equals 0. Such a potential could have this form where m squared is negative. And this leads to a renormalization group flow driven by a relevant operator with conformal dimension less than 3. The Euclidean evolution of the scale factor and the scalar field in the minus potential can be seen here. So essentially what happens is, so this is the scale factor as a function of time. Here we have the Euclidean ADS, we have an anti-friction part and the friction part. So the space-time shrinks and then we go to the minimum of the throat and then opens up again and we arrive at a local maximum where we can perform the analytic continuation and glue the Lorentzian part. Here we see the scalar field as a function of tau. So here is the anti-friction period where it accelerates, and here is the friction period where it decelerates and arrives at a constant value phi naught at the point where we can go to Lorentzian evolution and inflation can start. And here is the plot of the potential, of the minus potential as a function of the scalar field. Here is the anti-friction part, and here is the friction part. So the potential should contain a slow roll region for the scalar after the value phi naught here, so that the universe can subsequently inflate and expand in Lorentzian time. And our proposal is generic, so there should it can accommodate various models that are consistent with the latest experimental constraints of inflation, for example, the ones given by the Planck collaboration. So what did we gain by doing all these things, like using this Euclidean wormhole instead of the sphere? So we can again compute the semiclassical probability for this type of geometry and compare it with a no-boundary proposal. So to do this, we have to evaluate the Euclidean half wormhole on cell action. So we have to evaluate this. Since now we have a space-time with a boundary, we have to add the Gibor-Hawking term so that we have a well-defined variational problem. And since we're in Euclidean, since we're in the de Sitter space, we need to perform holographic normalization. So this is the term that contains the counter terms that one should add. And after we do this, we can either compute this numerically, or we can take some think wall approximations and do some analytic computations. And one typically finds a positive on cell action for the wormhole. So as in other holographic examples, due to the nice ADS asymptotics, we have a well-defined and well-behaved probability. So that is less than 1. So this way we can evade the problem with a no-boundary proposal that gave us a huge positive probability for a potential, for a universe that is empty. And now we can have a universe that nucleates high up at the potential and then follows this roll trajectory. There is a second issue with a non-boundary wave function, and this is that it is not normalizable. Our Wheeler-DeWitt equation, if we do the following redefinition for the scale factor avoids normal ordering issue, so it has a well-defined kinetic term that doesn't mix momentum with coordinates. But unfortunately, we cannot solve this equation in a closed form. But by work by Hawking and Page, it was shown that a similar equation admits a discrete set of normalizable solutions. And their idea is that semiclassical half-wormhole solutions can be seen as superposition of these elementary states. And if this is true, this could mean that the half-wormholes that we use here are described by a normalizable Wheeler-DeWitt equation. So this will be another nice feature that the no-boundary wave function doesn't have. But this we haven't checked. We should check it. It's just words at this point. We can also compute, apart from the wave function and probabilities, we can go and compute correlation functions. If we are at tau equal 0 and before, we can compute bulk correlators via the holographic process, and we can use the wave function here to compute the Euclidean path. Using the Euclidean path integral, we can compute the correlators. If we want to go to later times, so when we have analytically continue to Lorentzian time and compute cosmological correlators, we have to use the informalism or evolve the wave function in Lorentzian signature. Our construction, since it has ADS asymptotics, is possible to holographic interpretation and embedding. And from previous work we have in Euclidean ADS wormholes, we saw, so for Euclidean ADS wormholes, we have computed the correlation functions, and we can see that there exist cross-correlators that are non-zero. They have some specific features. They have a peak in the IR, and they go to 0 in the UV. And the way to describe such features from the quantum theoretic point of view is to have an effective non-local coupling between the two quantum field theories. So maybe these models for Euclidean wormholes, upon correct analytic continuation, could be used to describe these inflating cosmologies. And after analytic continuation, these cross-correlators could decode important information about inflation. But I should stress here that this is a phenomenological model. We don't have a string theoretic or UV complete picture that can give rise to such solutions at the moment. So, and there might be a tension between this slow roll region of the potential and Swampland criteria and bounds. So this is something that one should check carefully if one wants to have a complete UV picture. And let me flash here what we do at the moment. So as I said, our model is generic. It's just that the potential should have the features I described previously. So it will be interesting to see if there are realistic inflationary models that are in agreement with our proposal. And at the moment, we are taking Higgs inflation, which is a model that conforms well with experimental data. And the basic idea is that the Higgs boson, since the Higgs boson plays the role of the inflaton, which is reasonable because it's the only experimentally observed scalar particle in nature at the moment. These models include a non-minimal coupling term between the scalar, the Higgs, and the Ricci scalar. And then the Einstein-Higgs action is in the Jordan frame. And if we want to go back to the Einstein frame, we need to do a field redefinition for the Higgs particle. and a conformal transformation of the metric. And this leads to a potential that is of the slow roll type for large chi, and of the Higgs type for small chi. And the potential becomes negative for very large chi due to one-loop corrections of the standard model fields. Yes. That's true, but if you take the one-loop corrections, you can have a negative part, and if you have this negative part, then it goes to the class of potentials that I described. So we're taking this now. Yes, yes, it's a possibility. I would say yes. Oh, okay. Okay, that's interesting. Thank you. So let me summarize and tell you some future directions. So we proposed a new type of wave functions for the wave function of the universe, computed from the gravitational path integral with asymptotically Euclidean ADS boundary conditions. In the semiclassical limit, it describes a Euclidean half wormhole geometry. And if we put appropriate conditions on the scale factors such that it acquires a local maximum at the surface of reflection point, so in the middle, then we can analytically continue to Lorentzian signature and get an expanding universe. For this to happen, our class of models contains a non-trivial scalar potential that takes both positive and negative value. Our proposal evades some issues of the no boundary proposal, and especially it has a well-defined probability. And it also favors a long-lasting period of inflation for appropriate scalar potentials. And it raises the interesting possibility that we could use holographies, as we have ADS asymptotics, to understand inflationary cosmologies and perturbations. We would like, so here are the future directions. We would like to perform a thorough WKB analysis of the two-parameter Wheeler-DeWitt equation and study also the one-loop effects. It is important to understand whether the resulting half-wormhole wave function is normalizable or not. And we would like to analyze the spectrum of fluctuations around such half-wormholes. It would be interesting if it would be possible to embed our setup in a complete UV microscopic model. At the moment, we have some proposals about possible UV complete microscopic models that could give rise to Euclidean wormholes. So it will be interesting to see if these models, after analytic continuation, could also accommodate for cosmologies. But the most well-defined ones that we have are in lower dimensions. And it will be, and these two go together. This is an outcome of the other. It is to also understand what are our half wormholes from the dual field theory perspective in these more realistic higher dimensional models. Thank you.
Thank you very much, Olga, also for staying time. So we have some time for questions. Alberto, then Paolo.
In this wormhole solution, the curvature, invariant curvature, invariant. I was wondering if
What
it's
do you mean?
subplanetary or not. Did you compute that?
No, I didn't compute that.
Because, okay,
Why are you asking this?
I think it's important to know because if it is, for example, Planckian or transplanckian, then you be out of the regime of validity. The effective theory you are using because you're using Einstein Hilbert action,
Right?
Scalar field.
You can find such solutions semi-classically, and you can see that they are perturbatively stable. So I think you can safely use them.
Paolo and then Alessia.
When you said that Alex Vilenkin, the tunneling physics address, actually, I think it addressed, and you also quoted in your paper. I'm seeing your paper.
Yeah, okay, there are some. Mhm. Mhm. I agree. Thank you very much for your comments. Well, you need to have a specific potential to study those. We haven't. It's just my comment is just because there are some works that yeah, exactly. But I haven't checked specifically. Probably there is in these papers, like, but you need to. So you need to take specific models, I guess, to see the exact violation, right? I mean, these are work by Vafa et al. Yeah, but I don't have a specific model, but at least what I'm saying, to see the tension, you need to take specific models. Maybe for some models it's fine. Maybe some, yeah.
Jessica.
Mm-hmm. No, so what I present is everything anti-de Sitter. The idea is, since you have anti-de Sitter, can you use CFT to tell you something more? For example, for cosmological correlators that they are difficult to compute. Exactly. Yeah, this is, yes, just the setup, and I would like in the future to see if this you can see better. Okay, if for example one manages, so you don't, at least to my knowledge, there are no Euclidean AD solutions that come from supersymmetric theories, meaning that you need to somehow break supersymmetry, and then you lose control either on the one side of the duality or the other. At the moment, with my collaborators, actually, you can have some type of Euclidean wormhole solutions in type 2B string theory, that is dual to n equals 4, and they are half BPS. But there is a KFT, the two asymptotic boundaries are not really decoupled. There are 2 points that the boundaries connect, but there is still a throat that you can transverse to go to the one to the other. So this is a toy model for a Euclidean wormhole that preserves some supersymmetry. And in this case, it is known via localization that if you had one boundary and you have these half BPS solutions, they correspond to have a large Wilson loop in a large representation that back reacts in n equals 4. And this can be computed via localization from a Hermitian matrix model. And for this new type of solutions that they have the two asymptotic boundaries that they're connected, you can again compute via localization the answer, and essentially you have correlation between two Wilson loops that they are large, they backreact on the geometry, and they are one on top of the other at the boundaries. Now, if you go and separate these boundaries, you can write down a matrix model that could give rise to such solutions, and you can compute everything from the matrix model side of things. But because you are not 1/2 BPS anymore, you don't have an ansatz for the geometry, so you cannot go and compare the two sides. But if I had such a model and perform analytic continuation, cut it in half, and connect with the sitter, then I could use this to use holography and maybe learn something more about the early evolution of the universe, because in this case, you would have a really UV complete description. But at the moment, it's just a phenomenological model. But maybe with all these things I said now, could give something more interesting.
Mary?
See, I'm sorry for saying this word, a contradiction.
Okay.
The title of the talk, and I want your opinion.
Okay.
Cosmology from ABS. How distinct this go together? ABS is not the universe we live.
No, but it's the case that gravity is better understood at the moment. So by this,
sorry, no, I disagree.
You disagree, okay.
It's a very strong statement what you made right now.
Wait.
See, I cannot anti-deceit.
So I have anti-de-Sitter here in the very UV. Instead of having a sphere, why not have anti-de-Sitter?
But anti-de-Sitter is not the universe.
No, but but the universe that you see is from here up, and I say to you that with a appropriate potential, I can get the universe that you see.
Diverges with the positive cosmological.
Yes, there is a positive from exactly.
But can you tell more what's you said it, but what allows the sign change in the cosmological?
Yeah, you can have a potential that goes from negative to positive, and you can do this by relevant deformation. The problem
you do it by.
Yeah.
Like the city is a bubble inside an
No. It's like the no boundary, really like the no boundary, but I start from here.
With the wormhole.
With the wormhole, yes.
And it's crucial.
Yes, the wormhole is crucial. Otherwise, you don't get this. And also, it's crucial not just to have a wormhole, but to allow for a local maximum. Because I saw you before, you could also have the wormhole and have this picture that doesn't allow for inflation. You have only a Big Bang, Big Crunch universe.
I don't resist but to mention. So what we do is perform cosmology is to compute the transition amplitude from a contracting universe to an or to whatever state of the universe to another state of the universe. It could be contracting and expanding with a positive or negative cosmological constant. So seems to me. So but I mentioned this because something that is interesting in what we are seeing these days is the fact that even if you compute this kind of transitions, then that could be completely Lorentzian. So you start with one state, another state, and the amplitude is a completely Lorentzian amplitude, a completely Lorentzian action. But then you have some Euclidean components that appear. So namely, you need to include Euclidean geometries into your. So you sum over geometries that are Lorentzian, but there are also Euclidean geometries that comes into this. Do you see? Because so here there is the problem of passing from a boundary to this other proposal. Is there maybe something similar that is happening here? What you're adding?
Sorry.
Does it?
So you want to do a. Sorry, just to understand. You want to do as here that you sum over all compact matrix.
No, so
for your path integral to define the state? Is this a question or?
no, the question is more. So in your proposal, in which you go from anti-de Sitter to de Sitter, you solve some problems of.
Okay, maybe we can continue this discussion during coffee break or even after the coffee break, since it's more like technical. And I would
Thank you very
thank Olga
much.
again.
Thank you.